All right, so example 1 says to find the inverse. So what we're given here is an equation, and it says y equals 4x plus 2, and we're supposed to find the inverse of that equation. So we can think of this informally, if you want. Think of the x as the starting value or input, and you could just talk this out, right? So if you kind of follow the order of operations, if I take a number, namely x here, if I take a number, I multiply it by 4, and then I add 2. What would be the reverse of that, that sequence of actions? Well, if I multiplied by 4 and then I added 2, then I could subtract 2 and then divide by 4. And so you can think of inverses like that, but there is a procedure for finding the inverses, and since we know that a normal sequence of evaluating is the order of operations, we could just follow the reverse order of operations like we would solve an equation, and we could figure out what the inverse is. So steps to finding an inverse, the mechanical way is number 1, we're going to switch the x and the y. And actually switching the x and the y, or the domain and range, the input versus the output, actually immediately changes your equation into an inverse. So if I say y equals 4x plus 2, but I change that to x equals 4y plus 2, so that'd be the first step. This right here is the inverse, because we've switched the inputs and outputs. We switched the x and y. But after that, to make it look nicer, right, we want to then solve for y. Solve for the variable that isn't solved for. In this case, that would be y, which is typical in some math problems, but doesn't have to be. So x equals 4y plus 2. Now if we solve for y, just by solving the equations that you've done for so long is going to force you to do the reverse order of operations and do the inverses of all these things. So if I said, hey, solve for y here, you would say, okay, subtract 2. Exactly. So we'd do that, and we would get x minus 2 on this side equals 4y. And if I want to solve for y still, I'm going to divide by 4. And 4 divided by 4 is 1. And I have y equals total of x minus 2 all over 4. And so remember what we said before. We said we would subtract 2 and divide by 4, and that's exactly what this result is. We're taking x, we're subtracting 2, and then we're dividing by 4. And this is the inverse right here. So if you were to find the inverse of an equation, it's really all you do. You switch the x and the y, you switch those variables, and then you can just solve for the other one, because that's going to force you to do the inverse operations that you've done before, and it just gives you the answer. All right, you can go ahead and practice one of these. So y equals x squared plus 2. Go ahead and find the inverse equation of that. You can pause it. All right, so if I'm going to go ahead and find the inverse, I'm going to switch the x and the y. Force that issue first, and then I'm going to go ahead and solve for the y. So that's going to force me to do all these inverse operations. I'm going to subtract 2. I'm going to get x minus 2 equals y squared. And then I'm going to take a square root of both sides. And that would give me y equals the square root of x minus 2. And so there's the inverse. If I take something, square it, and add 2, the inverse of that is to take something, subtract 2, and then take a square root. It would do the exact opposite. So to get this idea here of what an inverse is, they do opposites, right? Let's think about for a second if we started with some input. Let's just say our input is 4. 4 is our input. And think about what would happen if we plugged in 4 into the original function, the original equation. And I'm going to use this concept of like a function machine that we talked about in the previous section here. Like we have an input and then we have an output that comes out of this thing. And so if we said that first equation that we're looking at is x squared plus 2, right? I'm going to take 4, I'm going to square it, I'm going to add 2, and I know I'm going to get 18 there. Okay, now we know, or at least we've stated that the inverse of that is what we just wrote down here, which is the square root of x minus 2, right? So if this is truly the inverse, that means that if I then took my output here, right, I plug in 4, I got 18. Now if I hit the undo button, right, if I take 18, you know, we plug that in, you know, this should give us back to the original input, right? So I have 4, I'm going to put that in green. So I take 4 and I plug it through the first function and I get 18. Now if I take 18 and run it through this so-called inverse that I just found out, which is the square root of x minus 2, it should give me back to 4, and it clearly does, right? Because if you were doing that, if you were to solve this expression here or evaluate this expression, root 18 minus 2, right? We'd take 18 minus 2 first, order of operations, and we'd get 16, and the square root of 16 is back to 4. So this is a clear indicator that these are indeed inverses. This is an inverse of this. Because if I take a number and I run it through that function and I get a number, 18 in this case, and then I run it through the inverse operations, I kind of go backwards and I reverse it, I'm ending up with the exact same number that I started with. And that's going to occur for no matter what x that I choose. If I choose 100 or if I choose 10, it doesn't matter. This intermediate step is going to spit out some number, and then I can immediately plug that into the inverse equation, and I will end up with what I started with. All right, so here's another practice problem. In this case, it is f of x equals 3x to the 5th minus 2. So I'm going to start this one for you because it's a little bit different. We're using function notation in this next practice problem. F of x, right? So you got to remember what function notation is. It's not y equals. We're saying, again, we talked about this in last videos, but we have a function named f, and the input is x, and we're saying this as f of x equals 3x to the 5th minus 2. But overall, this is really just the output. This is the output of the function after we plug in some x value into it. It's the result. So how do I find this inverse? It's going to be very similar to what we just did, except the notation can kind of mess people up. So the first step here is just to, you don't have to do this once you get good at it, but it's easy just to take this f of x, which is the output, and just switch it to a y to start with, at least in the first part. So we'll clearly show that those two things, f of x and y, are kind of doing the same thing or representing the same thing, the output. So now that I have that, I can go ahead and do the problem exactly the same as the last one. Switch my x and y, and I'm going to solve for y. So you can pause the video and see if you can finish this one up. Okay, so if I were to do this, I would then switch the input and output, switch the x and y. So you'd get that. And now at this stage, I'm going to go ahead and solve for the y right here. So this y right here, we have 3 different operations acting in this expression here in a specific order, which is the order of operations. But I'm going to go ahead and solve for y, so that will cause me to do the opposite, the inverse, or the reverse order of operations. So I'm going to do this, and I'm going to add 2 to both sides. I'll get x plus 2 equals 3 y to the 5th. And then if I'm getting y by itself, then I'm going to divide by 3. So then divide by 3. Divide everything by 3 on the left. So if I kept going, I have y to the 5th now equals x plus 2 over 3. And the last thing I'm going to do here is take a 5th root, right? So if I have something to the 5th, the inverse of that is the 5th root. I'm going to take a 5th root of both sides of that equation. And therefore, I'm going to get the 5th root of x plus 2 over 3 equals y. This is my, well, I shouldn't circle that yet. There's one extra thing you want to do here. So this right here, the sequence of operations, this is the inverse right there. But notice that the first thing that we started with, the original problem was written in function notation. It was f of x. And so what I'm going to do when I do this is I'm going to rewrite in function notation. So since I started with an f of x, I'm going to write this in function notation and say f of x equals the same thing, 5th root of x plus 2 divided by 3. But now this is the inverse, and so we can separate these two things. Instead of just saying f of x equals 3x to the 5th minus 2, we're not going to say f of x is equal to that same thing. We're going to distinguish the original from the inverse by putting a little raised to the negative 1 there on the f. So this right here, we're going to say, you would say that as f inverse is how you would say it, f inverse of x, because we'd put a little raised to the negative 1 there. Now that's not actually raised to the negative 1, it's just notation that is saying that we had a function f, and now this function is the inverse of f. So it's to distinguish it from the original function. So the proper answer here, the textbook answer here is going to be to say f inverse of x is the 5th root of x plus 2. Those two functions are going to do the exact opposite. Same idea as before. If we were to test this, if I plug in a number into this original function, right, let's just do that really quick in our heads. If I plug in 2, into x, I get 2 to the 5th, which is 32, and then times 3, which is 96, and then subtract 2, which is 94. So if I have 94, and let's say I plug it right back into this inverse function, I'd have 94 plus 2, which is 96, divided by 3, which is back to 32, and then I took a 5th root of 32, and that would get me right back to where I started, which is 2 in that case. So that's just the kind of the procedure you can use when you have an equation and you want to figure out the inverse of that equation.